Okay, the next few lessons are about making electricity with cells. The first one being about the electrode potentials. And as you know, in redox reactions, electrons move from one atom to another. And when electrons move, you get electricity, hence electrochemical cells. So our learning objectives for this video lesson are the following. First of all, we want to know and be able to use the conventional representation of cells, i.e. how to draw and represent a cell, common name battery. After we've done that, we want to know the IUPAC convention for writing half equations for the reactions that happen at each electrode of a cell. And lastly, we want to be able to use electrode potentials to calculate the electromotive force of a cell, i.e. the voltage of that cell. You'll probably have noticed that batteries that you have in your house might be listed as 1.5 volt batteries, and that would be the electromotive force or the EMF of that cell. Firstly, let's just consider the concept of electronegativity, which you may remember is the amount that an atom wants to attract an electron. And what we've got here is we've got a periodic table with the numbers in there. Instead of the atomic numbers and the mass numbers, we've got electronegativity numbers. These are numbers generated by a chemist called Pauling. So this is called the Pauling scale. And you can see that the most electronegative element in the periodic table is fluorine. I think you knew that, and that's got a electronegativity reading on the Pauling scale at least of 4.0. So that attracts electrons hugely. And of course, metals, on the other hand, they actually want to get rid of their electrons. They have a small number of electrons in their outer shell, and because of that, they want to get rid of it so then they can have a full outer shell by releasing their electrons. So their numbers, metals numbers, are generally lower than non-metals. So if you look in group 1, for example, you've got rubidium and cesium there at 0.8 and 0.7. So they are very low electronegativities. And sometimes a concept of electropositivity is referred to in terms of those very reactive metals. Now let's just consider copper and zinc, because they are two metals that are commonly used in cells. Now, copper has an electronegativity of 1.9 on the Pauling scale, and zinc has an electronegativity of 1.6. So you can see that copper wants electrons more than zinc does, or at least you can say, because it's a metal, at least you can say that copper minds receiving electrons less than zinc does. And so there's going to be a difference. There's a difference in electronegativity between copper and zinc, and that difference can be used to drive the flow of electrons, probably in this case from zinc to copper. So let's have a look in a bit more detail at making an electrochemical cell and the chemistry that goes on in the electrochemical cell. The chemistry is all about redox equations. That's why this lesson follows the one on redox equations. And so you're going to have both an oxidation reaction and a reduction reaction that's going to happen, and they're going to allow electrons to flow and make electricity. As I alluded to in the previous slide, an electrochemical cell can be made from two different metals, like copper and zinc, for example, that we mentioned. But they need to be dipped in salt solutions of their own ions. So if that was copper, it might be copper sulfate, and zinc might be dipped into zinc nitrate. And they also need to be connected by a wire through which the electrons will travel. And then the two solutions also need to be connected by what's called a salt bridge, which allows the charge to stay neutral. So let's have a look at a representation of a copper-nickel electrochemical cell. Here's a diagram of one. So here we have two half cells. Let me just draw what we mean by a half cell. So this would be a half cell, and this would be the other half cell, and those two together, they make the whole cell. So that's the half cell where oxidation goes on, and this is the half cell where reduction goes on. So let's consider the left-hand half cell first, and as we mentioned, we've got some zinc. So this electrode is just a strip of zinc metal, and it's in a solution of, let's say, zinc nitrate or zinc sulfate, doesn't matter what the anion is, to be honest. And in the other half cell we have the other metal, so this is copper in this case, so it's a copper strip, metallic copper strip, in a solution of usually copper sulfate, which just gives you copper ions in solution and sulfate ions. And then of course we've got the zinc ions in the left hand half cell and the copper ions in the right hand half cell. So as we mentioned in the previous slide when we looked at the electronegativities, zinc is less electronegative than copper, so it's going to release electrons more easily than copper, and that's why the electrons travel in this direction on the circuit. So obviously for electrons to flow we need the circuit to be complete, and so we've got a wire that connects the two electrons, and you can see the wire travels through a voltmeter because we might want to measure the amount of force that's applying to these electrons. And also the other way that the circuit is connected is by this salt bridge here, which is typically just filter paper soaked in often potassium nitrate. So let me just annotate that. You would get potassium nitrate, and that allows the circuit to be completed. Let me tell you why. Let's say in this case you've got zinc ions being created from the zinc metal. Then this solution would become more positive over time, in which case the electrons wouldn't leave the zinc metal because they would be attracted to the positively charged solution. And so what happens is that anions come out of the salt bridge, in this case it would be nitrate ions, come out of the salt bridge and neutralize the extra zinc ions that are coming into solution. And of course the opposite is going to happen here. What's happening here is we've got copper ions coming out of solution and forming copper metal on top of the copper electrode. So you're losing positively charged ions here. And so to replace the positively charged ions, you're going to get your positively charged ions coming from the salt bridge, just to maintain the charge. Otherwise, if this solution became negative, then these electrons that we want to travel in this direction would be traveling towards a negatively charged solution, and they would refrain from doing so, and we wouldn't get any electricity. Just going back to the zinc half cell, notice that we have the electrode is made of zinc, and as we've said before, the zinc is more willing to give up its electrons than the copper. So that's what it does. So if the zinc gives up its electrons, the electrons come off towards the copper in that direction. And if a zinc atom has lost its electrons, then it becomes a zinc ion, right? So the zinc ion comes off into solution and stays in solution there. So going back to the electrons come up and go through the voltmeter here and come down and then come onto the copper electrode. and so the copper electrode becomes negatively charged, which attracts the copper ions that are in solution. The copper ions are positive, they're attracted to these electrons that have come from the zinc, and they come out of solution, and they take those electrons from the electrode. And if a copper 2+ ions takes 2 electrons from the electrode, then of course it turns into copper metal, right? And then of course starts sticking to the outside of the electrode like that, and builds up as copper on the outside of the electrode like that. And so that's how we get our current. That's how we get our current. And one last point about the voltmeter. So the voltmeter is basically measuring the electromotive force, the force that is being applied to the electrons to move around the circuit, right? And that force is coming from the difference in willingness of zinc to give up their electrons and copper to give up their electrons. And if there's a big difference, there's a big force on those electrons. So if there's a big difference in reactivity of the two metals that form the electrodes, then there's a big force or electromotive force on those electrons. And so more electrons will travel around the circuit with a big electromotive force. All else being equal, of course. Okay, what we've been dealing with is one type of half cell that is a metal in a solution of its ions. We've seen zinc in a solution of zinc ions and copper in a solution of copper ions. That's one type of half cell. Another type of half cell is one like this, where you have in solution, you have Fe3+ ions and Fe2+ ions. And this time we're going to have a platinum electrode, because an electron has to be a solid that conducts electricity. And if a half cell doesn't contain anything like this, like here we would have just Fe2+ and Fe3+ ions in solution, so we've got no metal ion as an electrode. So if that's the case, then you can use something else, like platinum, for example, as an electrode. And platinum is used as an electrode for two reasons. One is that it conducts electricity, electrodes have to conduct electricity, and the second reason it's used is that it's inert. It's not reactive, it's not going to take part in any of these redox reactions. So the reaction that goes on here goes on at the surface of the platinum electrode. So at the surface, what can happen is we can either have Fe3+ gaining electrons, write it like that, to turn them into Fe2+ ions, or you can have Fe2+ ions losing electrons to become Fe3+ ions. So obviously if we are gaining electrons, this will be a reduction, or if we're going from Fe2+ to Fe3+, that's going to be an oxidation reaction. And which of these happens depends on what's on the other side, what the other cell is. So if this other cell is less reactive, say with less reactive than iron, then what happens is you're going to get Fe2+, they're going to be oxidized to Fe3+. It can be oxidized to Fe3+. However, if the other cell, if the other metal is more reactive than iron, then the opposite happens. You're going to get Fe3+ being reduced to Fe2+ at this electrode. So an example would be, an example of a less reactive metal than iron would be copper. Right, and an example of a more reactive metal than iron would be magnesium. Right, so if we had copper, you would get Fe2+, changing into Fe3+, and if we had the other cell made up of magnesium, then you'd have Fe3+ changing into Fe2+. And so the electrons would travel one way around the circuit with copper as the other cell, half cell, and they would travel the other way around the circuit if magnesium was the other cell, half cell.